Okay. I will go ahead and start. So again, the title of this paper is Unsupervised Data Augmentation, abbreviated UDA, and you can download it with this link. So by introduction, I'll go through the abstract. Deep learning needs large numbers of labeled examples to work well. So this would be supervised learning. Data augmentation has been used to increase the number of labeled examples by fabricating new data from existing labeled examples. So the implication is that in the past, data augmentation has been used on labeled examples. And in this paper, we want to extend that to the unlabeled portion of a data set. UDA, that's unsupervised data augmentation, can be used to utilize unlabeled data for training. So that's the main point of this paper, is applying this augmentation to unlabeled data to improve performance of a model. UDA enhances learning by encouraging the model predictions to be consistent between the unlabeled examples and its augmented version. So we'll go into detail on what we mean by consistent. And the results are that UDA leads to substantial improvements in accuracy on machine learning tasks. So again, we'll go into the details about the results of this research, but basically it's been applied to vision tasks and natural language tasks. In the vision domain, there's CFAR10 and SVHN, which is Street View House Numbers. Both of these are 10 class data sets. And the CFAR10 work involved using only 4,000 of the examples in CFAR10. It's much larger than that. But using only 4,000 of the examples, we can go from a baseline of 6.66% error to 5.27% error. And with the Street View house numbers, using only 1,000 examples, we can reduce the error rate from a baseline of 3.53 to 2.46%. In the language domain, one of the principal successes has been its application to the IMDb text classification. So that's it's a data set of movie reviews. And using only 20 labeled examples, it outperforms a model using 25,000 labeled examples. So this is quite dramatic. It's able to use less than 1,000th the number of labeled examples and work better. And then finally, another vision task is ImageNet. So using ImageNet, it adds an extra 1.3 million unlabeled examples. And it can then reduce the top 1 and top 5 performance statistics from 78.28 to 79.04 from a baseline, which is called the auto-augment baseline, which is a state-of-the-art baseline. And we'll go into much more detail on what auto-augment is. So a little bit more detail on to introduce the system. As I mentioned before, deep learning needs a large number of labeled examples to work well, but labeled data can be expensive. So in the past, semi-supervised learning has been used to make use of the unlabeled data and can be grouped into 3 areas of research. So there's the graph-based label propagation, graph convolutions, and graph embeddings, model prediction targets as latent variables, and consistency, smoothness enforcement. So the last one is where UDA inherited some of its techniques from. This smoothness enforcement has been shown to work well on many tasks. Smoothness enforcement forces the model to be less sensitive to small perturbations applied to examples through regularization. So the term perturbation is used in this paper, and it's a very kind of a general term, and augmentations is perhaps a more specific aspect of permutations. It has a slightly different meaning, which we'll talk about. And the examples that it applies to are both the labeled and the unlabeled examples. And again, the smoothness constrains the model's predictions to be less sensitive to perturbations of the examples. So the perturbations can be at the very front, or they can be within the model itself. So here is a very concrete example of perturbations of images. And this is from FastAI. FastAI has the ability to do perturbations within its software, and it's well integrated into the training process. So you can, here's a link to FastAI's image perturbations. So for images, we want to change the image in a semantically equivalent manner. We want to change the pixel values without changing the image's label. So here we have 8 examples of perhaps a single image, so 7 perturbations of a base image. Clearly they're all cats, but there's quite a bit of differences in the pixels. So here are a list of things that you might do to perturb an image. You can add noise, you can translate it, so you can shift the viewpoint within the image. You can magnify, so you can zoom in or out. You can rotate the image, and like an affine projection, so you can look at the image from an off-angle perspective. And then color modifications. You can change, for example, the illumination of the image. So there's, for images, quite a few possibilities for coming up with new images for training. But clearly, some of them are not semantically equivalent. Here's the term that's important here, semantically equivalent. For example, if we have pictures of signs with text in them, we wouldn't want to flip it, because you would make the text reversed, and so it wouldn't be semantically equivalent. And perhaps in this image of animals, if you rotated it 180 degrees, it would be upside down. And so that would not necessarily preserve the semantics. Also, you can do translations and move the focal point of the image or the subject of the image outside of the image. So not all perturbations are helpful. And so this paper attempts to learn good perturbations. And here's a little bit more detail about adding noise to an image, one of the perturbations we discussed before. And this is very early on. People added noise to signals to try to make the model more robust. And it has, in some domains, some usefulness, but and generally speaking, it's not a good way to do things. It can result in the image being corrupted. The main thing is the type of noise may not be natural and will result in a model that is not representative of the domain of interest. So another thing that we can do, if the domain is not vision, the other domain that we're going to talk about is natural language. So then the input to the model is text strings, typically. So in applying data augmentation to natural language, we wish to create a set of sentences with identical deep structure, but different surface structure. So those are kind of linguistic terms, but here's a concrete example. We might have, for example, the sentence, Charles broke the window. But a perturbation of that sentence could be, the window was broken by Charles, which is a passive transformation of the sentence. And another possible perturbation, it was Charles that broke the window. So we've managed to triple our data set of text using this perturbation. So next, I would like to go over the background of supervised data augmentation. So this paper, of course, is UDA, unsupervised data augmentation, but a simpler place to start and perhaps the precursor to this in terms of research was supervised data augmentation. And this slide also has an introduction to the mathematical notation that's used in the paper, so it's worth kind of going through it, even though it's a little bit basic. Again, data augmentation aims to create a novel and plausible training and plausible training data by applying transforms to the data without changing its class or nature. So the data augmentations that we're interested in are semantic equivalence. So, and to describe the notation in the paper, they use X as an example. So that typically that's the input to the model, X. So X would be an image, or it might be a string of tokens from a natural language, words. And then y of x, a function of x, also used, denoted as y star, is the label of x. So the ground truth of x, we're going to use y star throughout the paper. And we're interested in learning a model, p theta y given x, to predict y star based on the input x, where theta denotes the model parameters. So this is a notation of a conditional probability density. But the realization of that conditional probability density is going to be a deep neural network, or some variants of that. But the fundamental components within this density model are deep learning networks. And so theta, in this case, is going to be the weights and biases of the deep learning network. Okay, so the next mathematical object is another conditional distribution. That's Q of x hat given x. And this is the conditional distribution of the augmentations of an example x. So what we have here is, you can think of this as a generator of augmentations. It statistically or probabilistically perhaps generates augmentations from a base image x. Within FastAI, you have some of this built in. You can specify within a type of augmentation the statistical parameters. Typically, those are bounds on the parameters, and perhaps it's uniformly distributed. For example, rotation, you might say plus and minus 30 degrees with a uniform distribution throughout that. So that would be something FastAI can do, but it's perhaps basic. We're going to look at more compositions of those, which FastAI can do as well. So then this is another important point, that we want these augmentations to be valid in that after augmenting the data, the label of the data should remain the same. So mathematically, that is, the notation is that y of x, the label of x, should be equal to the augmented version of the x, its label. So another notation that's used is L and U. Capital L is the set of labeled data, and capital U is the set of unlabeled data. So then, supervised training with augmentation is done by minimizing the objective function below. So let's go through this equation because it's built upon in UDA. So we see two expectations, an outer expectation and an inner expectation. The outer expectation is essentially a mean over L, so a mean over the labeled data. Whereas the inner expectation is a mean over the augmentations. So we see that a labeled data point X is supplied to this augmenter, and it probabilistically produces an augmentation, and then that's averaged over this loss function. And that's what we're trying to minimize. This is our objective function. In the case of supervised data augmentation, you see that it's supervised here because all the data comes from L, the labeled data set. So we can essentially learn by finding the theta that minimizes this objective function. So that's the machine learning aspect of this. And DA, that stands for data augmentation. And again, these are the parameters of the model, which in the case of the neural network that we're going to implement this with is going to be weights and biases. Okay, so a little bit more about augmentation, specifically task-specific augmentation. So auto-augmentation for image classification. Now there's specifically a piece of software called auto-augment, and it's used to find the best augmentations for the training set. Now, here's a link to the auto-augment paper, and one of the authors of this paper is also an author for the UDA paper that we're talking about now. Auto-augment is used as a baseline, but the code within it is also modified to work within UDA itself. So it might be helpful at some point if you're going into the details of this to read that paper. So another task besides vision is we talked about text classification. So specifically in the UDA paper, they want to use back translation for text augmentation. So this is an interesting idea. So sentences in the training data are translated into French and then translated back to English, producing a perturbed version of the original text. And the perturbations are adjusted by using some random sampling and softmax temperature decoding techniques that are available within the translator. So the translator is not simply like a one-to-one transform between an English sentence and a French sentence. There's some one-to-many methods of the transform. So that allows it to be used to generate perturbations of text. Another technique that they talk about for text is term frequency inverse document frequency based word replacement. So rather than a simple method of generating augmentations, not a very good one, but is simply you take the text and you replace words, perhaps randomly, with synonyms of those words. But the main problem of that is that you can replace keywords and completely change the semantic equivalence of the sentence. So by using these term frequency, inverse document frequency statistics of words, you can allow that the keywords to be preserved, but the low TF, IDF scored words would be replaced more readily. So we get some augmentation of text, but preserving the semantic value of it. So auto-augment, this is a slide to go just to describe how auto-augment works. And I'll just go over this very quickly since there's a whole paper just on auto-augmentation. But from the paper, it's a simple procedure that automatically searches for improved data augmentation policies. So in its implementation, the authors of that have designed a search space where a policy consists of many sub-policies, and one of them is randomly chosen for each image in the mini batch. And then this sub-policy has two operations, each operation being an image processing function, such as what we've talked about before: translations, rotations, shearings, and a probability and magnitudes of which those functions are applied. We talked about magnitudes, perhaps, in terms of scaling parameter or rotation parameters, the magnitudes of those, and the probabilities were also considered to be part of that search space. And so auto-augmentation uses a search algorithm to find the best policy such that a neural network yields the highest validation accuracy on a target data set. So this was originally developed as a supervised data augmentation. And so we'll go look at a benchmark for that. And but the authors of this UDA paper used that software as their vision augmenter with changes. So I'll begin with an overview in this slide of UDA, unsupervised data augmentation method. So data augmentation has been previously applied to labeled data, and it resulted in significant improvements. Often large amounts of unlabeled data is available, but the cost of labeling it is prohibitive. So in UDA, we have the potential to work much better. It has the potential to work much better than the standard supervised data augmentation. But because it can utilize the unlabeled data, which may be much more plentiful. And the technique that's used is that UDA models are trained to minimize the KL divergence between model predictions on the original data and model predictions on the augmented data. So we'll look at the equation of this minimization involving the KL divergence, which is a measure of the difference of two probability densities. So another introductory slide, which previous research that was done was perturbation-based. So as an introduction to the augmentation-based, I'll just, the paper goes over this, it's perhaps good to introduce it. So if we're given an input X, we compute the output distributions given X. So this is this P of theta Y given X. So basically we use the neural network to do a prediction. And we also compute this same distribution from a perturbed version of the data. So now this density is conditioned on X and epsilon. So this is a perhaps noise parameter. So in the past, noise has been added, say, from images to the front end, or it can be added to the model itself, and perhaps in the form of dropout or noise in the weights. But the key idea here is we enforce this smoothness by minimizing the divergence, the KL divergence between the two distributions. So this is the mathematical notation that's used. the divergence, this KL divergence, it has essentially two inputs, two probability distributions, and then it produces a scalar, a number that gives a measure of how similar those, how much they diverge. If they're identical, they diverge by 0, so that's the minimum. KL is always greater than or equal to 0, and then it goes up from there. You know, there's no bounds on it. So this minimization of divergence will force the model to be insensitive to perturbations and hence smooth with respect to changes in the image. So now UDA wants to specifically do something more than just a perturbation. It wants to use augmentations. And again, as in the last slide, model training is done by minimizing the KL divergence between an unlabeled example and an augmented unlabeled example. Well, that's what we're doing in UDA that's different. And if you look at this equation compared to our previous supervised equations, there's some similarities. There are these nested, an outer expectation and an inner expectation, but now the argument of the expectations, you know, is the KL divergence. And the outer expectation, as you see here, is X over within U, the unlabeled portion of the training set. So that was different. Before it was X element of L. So now, you know, we're using the unlabeled data, but the inner expectation is the same. We're using this augmentation distribution to generate our augmentation. So the UDA wants, this is a term within UDA training, is this UDA term here, objective function. So this slide from the paper combines both the labeled aspect of training on the left with the unlabeled aspect of training on the right. So I'll go through this in detail. I think it's useful. And so on the left here, we have our L, set L, you know, the labeled data, the X, you know, data itself, and its labels. And we use the model, which, you know, is going to be a neural network, deep neural network, or variant. And which implements this probability, this conditional probability with our theta parameters. And we compute a supervised cross entropy loss. So that's one component of the final loss. And on the right is the unsupervised portion of the algorithm. So here we have X as an unlabeled data point. So notice there's no Y on the right-hand portion of this. There's no Y star, there are no labels. So Y goes through M, X goes through M, just as it does on the left. However, X also goes through an augmentation. And the augmentation is very specific to the domain. We talked about specifically the back translation, you know, English to French, French to English is one. Auto augmentation, the algorithm described in a paper, for vision, and the term frequency, inverse document frequency, word replacement algorithm. So these are possibilities depending on the domain. That produces this X hat, this augmented version of the input X. And then that goes through our model, just as X did. And then, so we have two probability densities. And this unsupervised consistency loss, this is our KL divergence from the equation before. So we combine these two losses by weighting them, simply adding them together, weighting them, multiplying by some, alpha, 1 minus alpha kind of thing, and summing them together to get the final loss. So this is the entire system for training UDA. And I'll just go through this quickly, but the authors of the paper developed another technique of training, signal annealing, TSA. And that makes up for issues with the imbalance between labeled and unlabeled data. It compensates for that. So UDA makes the use of unlabeled data, which is typically more readily available than the labeled data. So more training data allows for large models with many parameters. But the imbalance between these two types of data leads to issues during training where the labeled data can overfit the model. So TSA adjusts the number of labeled samples used during a training step to prevent this overfitting. Label examples within a mini batch B are selected for use based on the probability calculated by the current model. So this top equation here, that is what is being done. This I is the indicator function. It returns a 0 or a 1 based on the truth or falseness of this argument. So NT is this threshold that's going to be adjusted over time monotonically. So that is the threshold, and this is the threshold is calculated using this lambda of T, which can have different forms. But basically, as NT is increased, more labels examples are used. And then Z in this equation is simply a normalization factor that counts the number of samples that were met this threshold criterion. So then finally, the training process, these are perhaps the epochs, starting from the beginning and going to the end. So at first, lambda T is 0, and then it monotonically increases to 1. And the effect of that is that NT changes as well. And it goes from a low value, N of T would go a low value of 1 over K. Now, K is the number of classes in a particular data set. And so that's, 1 over K, like if it's a 2-class problem, it's 1/2. So it begins at 1 over K and ends at 1. And so then there are 3 types of lambda schedule curves, and they can be used depending on the difficulty of the problem and the number of labeled examples. So this TSA is an algorithm they developed specifically for UDA to get around the problem of imbalance between labeled and unlabeled data. So the last part of the presentation and the paper is going to be on the results of experiments. And the first thing we'll cover are the language experiments. So there are 6 data sets used in the language experiments. IMDb, Yelp 2 and 5, Amazon 2 and 5, and DBpedia. So briefly, the first 5 are sentiment tasks. IMDb is 2, maybe just positive or negative sentiment. So 2 versions of Yelp, like a binary version and maybe a 5-class version, which is perhaps stars, maybe a number of ratings. Amazon, a similar. And then finally, we have the DBpedia, which is based on Wikipedia topics, and that has 14 classes. So the language model that's going to be used in these experiments is BERT, which stands for Bidirectional Encoder Representations from Transforms. So BERT is based on transformers, and transformers are a type of attention mechanism, and they've been shown to work well, and they perhaps are an alternate to something like a recurrent neural network, an RNN. So they've been used in the place of those kinds of things. So BERT is implemented with TensorFlow library, and I think it's tensor to tensor is what it's based on. So BERT has a couple of different models available. There's the base version, which has 110 million parameters. And then there's the large version with 340 million parameters. So those parameters are then trained on 2 data sets, the book corpus, which has 800 million words, and Wikipedia corpus, which has 2.5 billion words. So that's a lot of data, and it takes that in order to get good estimates of these large numbers of parameters. So BERT is going to be what these language experiments use. And another aspect of it that's good is that it's perhaps analogous to something FastAI has, in that for a vision model, you have say you have a custom head, and then you have the convolutional parts of the model. So and then you can freeze the model and only train the custom head. So it's a type of transfer learning. You might take ImageNet, ResNet model, and then unfreeze the custom head and just train that. And this BERT is analogous to that in that it's been pre-trained, but there is a final layer at the end, at the top, perhaps near the output, that can be fine-tuned. And so it's useful for a lot of natural language, improving the performance. So here are our language results. The first part, the top of this, is our fully supervised baseline. And here are 6 data sets. And here are the number of supervised examples. So 25,000 for the IMDb. So pre-BERT, the state-of-the-art, SOTA, state-of-the-art, was 4.3% error rate. But BERT large does 4.51, so pretty close. However, if you look at all the others, BERT is superior. So in some, I guess you would say, BERT is now maybe the state-of-the-art. So those are the baselines using fully supervised data. So in some cases, it's quite a bit of data, 560K, for example, here. So we're going to use the BERT, and we're going to use different versions of BERT, and then we're going to use it with and without UDA and see how it performs. So IMDb, we're only going to use 20 labeled examples. So that's 20, whereas the baseline had 25,000. So this is at the very beginning of in the abstract, they noted this as being a dramatic improvement. So what we can see is, well, there's different versions of BERT. Random is not so good. I mean, it's basically not initializing. But BERT base, I've talked about that. That's the 110 million parameter version. And BERT large is the 340 million, I believe, parameter version. And then BERT fine-tuned is BERT large that's been fine-tuned to the specific data set. So we can see that it starts out pretty bad, 43% error. But with UDA, we can lower that significantly. But with BERT base, we start out at 27.5 because we're only using 20 examples, 20 labeled examples. But using UDA and taking advantage of the unlabeled data, we can significantly lower the error rate to 4.78%. And finally, BERT fine-tuning, which is specific to this data set, lowers it even more to 4.2% error. So those types of improvements are across the board here. We see that BERT fine-tuned with UDA is shown, is bold on every one of these, except the last one, which they didn't run it on, but it does well on the large. It's very good. I mean, when you consider the small amount of labels that are used. And the reason, so there's 20 because there's two classes. So there's 10 each, again, 10 each. Here, the 5 class, it has more per class, more difficult problems. So there's more labeled, again, 20. And DBpedia, there are, 140 because there are 14 classes in that. All right, so we're going to move our experiments next to vision. And I'm just going to briefly talk about these two tasks, CFAR 10. That's 10 classes, and here's an example of what they look like. And the other vision data set is street view house numbers. And again, it's 10 classes. It's sort of like, digit recognition, but they can look, like images. So there's, so you're actually, the data set is actually what's in blue here, what's in the bounding boxes. It's not the whole image, it's just these individual images. So here are the vision experimental results. There are 2 columns, one for each of the data sets. So the very first line is the baseline of supervised training. So that means we just, in CFAR 10, we just simply take 4,000 labeled images and we train it and then test on, out of training data. And we see that we get 20.26% error. And then they did this 10 times, so they're able to compute this is the average over those 10 times. And they're able to compute a standard deviation from those 10 training runs or experiments. So that gives you some confidence, bounds on that. So then the next line is auto augmentation. So again, that's applying the paper by one of the authors to be labeled training data. And that creates a significant reduction. So you're creating more, instead of 4,000 training examples, you now have multiples of that. And that improves things dramatically over supervised but unaugmented baseline. So then the next several lines are, this is, a highly benchmark problem. So many people have tried to use this identical data set and improve the performance. And so, the pseudo label people did better than the supervised baseline. Pi models, the mean teacher is another technique. VAT and variations of VAT, have lowered all these things, mix up, and then ICT. I won't go into the details of how these work, but at the very end, we see UDA is able to beat everything. So it's a substantial reduction from the supervised baseline. So that's true in both vision tasks. So the other vision task, different from the other two, is the ImageNet data set. So that has 1,000 classes and 1 million labeled images. And so they applied UDA to this data set. And the first thing they did was use the ResNet 50 model, but only use 10% of the data. And their ImageNet typically has two statistics, the top one and the top 5 accuracy. So here are the numbers. But after using UDA, the UDA algorithm, we can reduce that. Still, it's a ResNet 50 model, but it's using unlabeled data to improve that. And it's significant. So the 10% of the data is used as labeled examples, and unlabeled data is chosen from the other 90%. Okay. So in the lower portion of this slide is how it works, how you can use all the image data, all 1 million ImageNet images, but then use extra unlabeled data. So just a note, ResNet 50 has 2.56 million parameters. So the data set that's going to be used for augmentation is an out-of-domain data set called JFT. They are not necessarily from the same classes as ImageNet. They're definitely images, but they're not, these 1,000 images, not specifically that. So they're out of domain. So we want to bring a portion of those in to our unsupervised method, and we're going to do that by using, by picking 1,300 of the most probable images for each of the 1,000 classes in ImageNet. So we simply use our ResNet 50 model, pre-trained on ImageNet, calculate these probabilities of each of those, and pick the top 1,300 from each one. Now we've assembled an unlabeled data set, and we can use it in UDA. So here are the performance numbers. ResNet 50, it has this top 1 accuracy of, these are accuracy, 71%, and the top 5, which is typically another way that ImageNet is scored, 93.73%. So auto augmentation, that's a baseline. It has an improvement of 1%, and small 0.5% maybe improvement here. And UDA improves upon that as well, upon augmentation. And these are very small improvements, I would say. I mean, but, you know, it's a very hard problem. And, you know, it's relevant to make improvements in ImageNet. So finally, I will go over the conclusions from the paper. So I'm just going to essentially just read their conclusions because I think they're very succinct. So I'll read it as if it's written by them. In this paper, we show that data augmentation and semi-supervised learning are well connected. Better data augmentation can lead to significantly better semi-supervised learning. Point number 2, our method, UDA, employs highly targeted data augmentations to generate diverse and realistic perturbations and enforces the model to be smooth with respect to these perturbations. And they also, we proposed a technique called TSA, and it can effectively prevent UDA from overfitting the supervised data when a lot more unlabeled data is available. For text data, UDA is very effective in low data regime, where state-of-the-art performance is achieved on IMDb with only 20 examples. So that is, I think, very impressive. For vision, UDA reduces error rates by more than 30% in the heavily benchmarked semi-supervised learning setups. Again, 30% is good. And lastly, we have our ImageNet experiments. UDA can effectively leverage out-of-domain unlabeled data and achieve improved performances on ImageNet, where we have large amounts of supervised data. So those are the conclusions. And so my conclusion is that this works very well. The code for this has not been released. It will be released according to the authors. And so I think when that code comes out, it'll make some of the details that are a little bit vague apparent. But I think that, you know, even though you're using a small amount of labeled data, you're using a large amount of unlabeled data. So it's computational. In fact, the processing of those unlabeled data for the training for that is probably quite computational. So you're basically making a big substitution of human labeling time for machine learning time. So that's a trade-off, but I guess that's the whole point of AI and machine learning, is to do that substitution. So that's it. Thank you for listening. Any questions, just send me a message. Thank you.